Welcome to the paper of Numerical Methods in the subject of Information Technology under EPG Pathshala. In our previous module, we learned about Trapezoidal Rule as a particular case of Newton-Cotes integration formulas. Trapezoidal Rule was obtained by approximating function by a straight line, that is the n equal to 1 linear polynomial, and this linear polynomial was integrated to get the estimate of the integral. We found the trapezoidal rule to be very simple, convenient to apply, and to increase the accuracy we applied the composite form of trapezoidal rule. Nevertheless, the number of subdivisions needed were very high because the error term is of the order of h square, where h is the subinterval size, and as a result the number of subdivisions required were very high. And so if the function is computationally complex, then lot of number of function evaluations are needed to reach the desired accuracy, and moreover the rounding of error also may start playing a dominant role. So why not explore the possibility of approximating function by a higher degree polynomial and use the integral of that polynomial as an estimate of the integral of the function. So today we will explore that. The general Newton-Cotes formulas are obtained by the technique of approximating function by a polynomial of degree n, and this polynomial is integrated to get the estimate of the integral. And in Newton-Cotes formulas, see, the formula as we have already seen is of the form of sigma I equal to 0 to n wi fxi, where wi's are the weights and abscissas x0, x1, x2, xn are already assumed to be fixed. We approximate the function by Lagrange's interpolating polynomial. So fx is approximately equal to Pnx, where Pnx is equal to sigma I equal to 0 to n Lix yi. Yi is being written for fxi. Now these Lix are the Lagrange's coefficients, and Lix are given by the numerator in the Lix is pi stands for product of the factors x minus xj, where j runs from 0 to n, j different from I. That is, it is product of the factors x minus x0, x minus x1, so on x minus xn. It contains all the factors in the product except x minus xi. For example, L0x will be x minus x1, x minus x2, x minus xn. It will not contain the factor x minus x0. L1x will be x minus x0, x minus x2, x minus x3, x minus xn. It contains all the factors except x minus x1. And so in general Lix, the numerator contains all the factors x minus x0, x minus x1 up to x minus xi minus 1, and then again x minus xi plus 1 up to x minus xn. It will not contain the factor x minus xi. And so in the compact notation, we can write the numerator as pi j equal to 0 to n x minus xj, where j is different from I. And denominator is just obtained by substituting the numerator x equal to xi. So for example, L0x will be x minus x1, x minus x2, x minus xn, and denominator will be, you substitute x equal to x0, so we get x0 minus x1, x0 minus x2, x0 minus x3 and x0 minus xn. So in compact notation, Lix can be simply written as product x minus xj, j runs from 0 to n, divided by product xi minus xj, again j runs from 0 to n, and where j is different from I. And we need to integrate this polynomial. A to b Pnx dx will be our approximation for the integral. And so this a to b Pnx dx needs to be written as sigma wi yi. So sigma wi yi, I runs from 0 to n, is equal to a to b Lix yi dx. Now yi's are constant and integral of the sum is sum of the integrals, and so we can write this as summation sign outside sigma I equal to 0 to n yi into the integral a to b Lix dx. So we need to now derive the integral a to b Lix dx. Let us focus on integral of a to b Lix dx. For convenience, let us assume that these points x0, x1, x2, xn are uniformly spaced, and so the distance between any two consecutive xi's is h. So xi minus 1 is equal to h. And so if we are dividing the interval AB into n parts, our h is b minus a by n. So we have n plus 1 points x0, x1, x2, xn. H is b minus a by n. A is equal to x0, b is equal to xn, and we can say that a is x0 less than equal to x1 less than equal to x2, so on, less than equal to xi less than equal to xi plus 1 dot 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 less than equal to xn. Now today we would like to derive the general form of Newton-Cotes formulas and then take particular cases n equal to 2 and n equal to 3 separately. That is, when we approximate function by quadratic polynomial, and the next case when we approximate function by cubic polynomial. And so it will reduce to our work of calculation of the Cotes coefficients to almost half, because if we know if our n is 3, if we know 3c0, we know 3c3 also, if we know 3c1, we know 3c2 also. So instead of calculating 4 Newton-Cotes coefficients, we will be required to only 2 Cotes coefficients using this property NCi equal to NCn minus I. Now for convenience, let us assume the points are equidistant, and in this case our x0 a is x0, x1 is a0 plus h, x2 is a0 plus 2h, so on, xi is a0 plus ih, xn is a0 plus nh, and so let us calculate the denominator first. The denominator is product of xi minus xj. Xi is a0 plus ih, xj is a0 plus jh. So xi minus xj is nothing but I minus j into h. x0 cancels. And so denominator is a product of the terms I minus j into h, where j is different from I. And numerator is product of x minus xj's. Now x is any point in the interval AB. I can express x as a plus th, where t ranges from 0 to n. When x is a, t is 0. When x is x1, t is 1. When x is x2, t is 2, and so on. When x is xi, t will be I. In general, I can express x as a plus th. So now let us simplify. The numerator is all the factors of the form x minus xj. So x is a plus th we have expressed, xj is a plus jh. So x minus xj becomes a cancels, t minus j into h. So numerator is product j equal to 0 to n, x minus xj, j different from I, and that becomes product j equal to 0 to n, t minus j. H comes outside, every has h common, there are n factors, so I can say h raised to n pi product j equal to 0 to n t minus j, and that divided by t minus I. So this is the numerator. Let us similarly simplify the denominator terms also. Now these denominator terms, see xi minus xj's are I minus j into h, that we have seen. Now let us divide this denominator terms in two parts. One, product j equal to 0 to I minus 1 xi minus xj, and the second j equal to I plus 1 to n xi minus xj. Now these terms j equal to 0 to I minus 1 xi minus xj give product of I minus j, j runs from 0 to I minus 1. Let us substitute one by one. J is 0, I get I, j is 1, I get I minus 1, j is 2, I get I minus 3. So this goes from I minus 1 into I minus 2 up to finally when j is I minus 1, I get I minus I minus 1, that gives me 1. So it is I into I minus 1 up to 1. Now second factor, j is from I plus 1 to n, xi minus xj. So this is here j is I plus 1. So I get I minus I plus 1, which is minus 1. Next term is j will be I plus 2. So the next term is I minus I plus 2. So this will give minus 2 and so on. So I get minus 1, minus 2, minus 3 up to finally j is n. So it is I minus n, or that we can write as minus of n minus I. And all these terms, h of course is common there. So we get the result. This is I to 1, I into I minus 1 up to 1 gives me I factorial. And here in minus 1, minus 2, minus n minus I, there are n minus I terms. Minus 1 common from each of the term, we get minus 1 raised to n minus I, and then the factors are 1 into 2 into 3 up to n minus I. So that is n minus I factorial. So denominator is I factorial minus 1 raised to n minus I, n minus I factorial h raised to n. And so when we combine the numerator and denominator, our LIX becomes, numerator is product j equal to 0 to n t minus j upon t minus I, and minus 1 raised to n minus I factorial, n minus I factorial. So our wi's are given by a to b LIX dx, and that let us simplify it. Substituting x is a plus th, so we get, and when x is a, t is 0, when x is b, t is n, and dx becomes h dt. Power of h has already cancelled, so 1 h we get outside. So all the constant terms we take outside, h minus 1 raised to n minus I upon I factorial, n minus I factorial, and inside the integral sign we get 0 to n. Numerator is products t minus j, j runs from 0 to n, and denominator is t minus I dt. Basically it is only the terms t minus 1, t minus 2, t minus n except the factor t minus I, and that we are expressing as if it is pi j equal to 0 to n t minus j upon t minus I dt. Now this is the formula for the weights, and so our general form of Newton-Cotes integration formula, where you are approximating function by a polynomial of degree n, is given by integral a to b fx dx, can be approximated by sigma wi yi, where wi's are the weights. Now these weights wi's let us express as nh into nci. So if we express wi's as nh into nci, h is already there, so we have to multiply and divide by n. So nci become minus 1 raised to n minus I upon n I factorial, n minus I factorial, 0 to n t into t minus 1 t minus n upon t minus I dt. These NCIs are called Cotes coefficients, Newton-Cotes coefficients. And these Newton-Cotes coefficients, the weights are given by in terms of the Newton-Cotes coefficients as NH into NCI. NH is nothing but the length of the interval of integration a to b, because h is b minus a by n, and n is standing for the degree of polynomial of approximation. Now before we proceed further, let us determine two very important properties of these Cotes coefficients, because which should come very handy for us in calculation of these Cotes coefficients and deriving the integration formula for n equal to 2 and n equal to 3. Now first very important property of these Cotes coefficients is that summation of NCIs is always 1. This can be verified very easily. See our formula, the a to b fx dx is equal to a to b pnx dx, that is sigma wi fxi plus the error term. Now error term has the form fn plus 1 at the point xi by n plus 1 factorial x minus x0, x minus x1, x minus xn. So this n plus 1 derivative would be 0 for n greater than or equal to 1, and so its integral is also 0. So error term is 0, the first derivative is 0, and definite integral of a 0 is going to be 0. and therefore we can say that our integral formula gives exact result when fx is constant. Let us say fx equal to 1. So if fx is 1, a to b fx dx is a to b 1 dx is b minus a, that is equal to nh, and our Newton-Cotes integration formula is nh nci nh into sigma nci yi, because the integration formula is sigma wi yi and wi's are nh into nci. So if we compare both the sides, left side is b minus a and right side is nh summation I equal to 0 to n nci y's are 1. B minus is nh, it cancels on both the sides, and so we get summation nci's is 1. So the sum of the Newton-Cotes coefficient is always 1, and we can use this to get easy calculations. Other important property shared by these Newton-Cotes coefficients, and that is nci's are equal to nc n minus I. In other words, like suppose our n is 5, 5c0 will be 5c5, 5c1 will be 5c4, like binomial coefficients. 5c3 will be 5c2 and so on. And so it will reduce to our work of calculation of the Cotes coefficients to almost half. Because if we know, if our n is 3, if we know 3c0, we know 3c3 also. If we know 3c1, we know 3c2 also. So instead of calculating 4 Newton-Cotes coefficients, we would be required to only 2 Cotes coefficients using this property nci equal to nc n minus I. Now this property nci equal to nc n minus I can be derived very easily. Look at the form of nci's. In this integral of nci, which is given by minus 1 raised to n minus I upon n, I factorial n minus I factorial 0 to n t minus 1 up to t minus n upon t minus I dt, we change the variable of integration from t to another variable u, and this u we express as n minus t. That is, our t is equal to n minus u, dt is minus du. When t is 0, u will be n. When t is n, u will be 0. And using it, our nci's will come out to be minus 1 raised to n minus I upon n, I factorial n minus I factorial constants as they are. Limit of the integration becomes now n to 0, and the expressions become n minus u, because t is n minus u now, n minus u minus 1, n minus u minus 2, so on up to finally n minus u minus n, that is minus u. dt is minus du, so minus du, and denominator becomes n minus u minus I. Taking minus 1 common from each of these terms in the numerator and also minus 1 common from the denominator, we get minus 1 raised to n outside, and inside the integral sign we get u minus 1, u minus n upon u minus in the bracket n minus I du. And so this nci becomes minus 1 raised to minus I, which can be written as n minus in the bracket n minus I. See, minus 1 raised to minus k is same as minus 1 raised to k. So minus 1 raised to minus I can write as minus 1 raised to n minus I. Minus 1 raised to 2n was 1. So we get minus 1 raised to minus I n minus I factorial integral 0 to n u minus 1 u minus n du upon u minus n minus I, and that is the expression for nc n minus I. So this gives us that nci's is nc n minus I and summation of nci's are 1. So these two properties will ease out our calculations of the coefficients of the weights wi's in our further work. Now before we proceed further, let us verify for the case n equal to 1, which we have already studied. If I put n equal to 1, our integration formula becomes a to b fx dx is to be approximated by w0 fx0 plus w1 fx1, where w0 is nh nc0 and w1 is nh nc1, where n is 1. So w0 becomes h into 1c0 and w1 becomes h into 1c1. We need not derive 1C0 and 1C1 from the integration expression. We can use these two properties. 1C0 is same as 1C1 and summation of these two has to be 1. 1C0 plus 1C1 has to be equal to 1, and so we get 1C0 is equal to 1C1 equal to half. And so the formula is a to b fx dx is h by 2, h is b minus a by 2. So h by 2 fx0 plus fx1, and that is the same as the trapezoidal rule which we had derived in our previous module from scratch. Now with this, let us proceed ahead. Let us take the case n equal to 2, meaning by we are approximating function by quadratic. 3 interpolating points. Our a is x0, b is x2 now, and x1 is the midpoint of the interval, and h will be b minus a by 2. x1 minus x0 is h, x2 minus x1 is h, h is b minus a by 2. So the formula which we have developed just now, let us apply that formula. So a to b fx dx is approximated now by sigma I equal to 0 to 2 wi fxi, and now this wi weight is given by nh nci. n is 2 now, so it is 2h 2ci. I runs from 0 to 2. I is 0, 1 and 2. Now 2ci we need to find out the values for I equal to 0, 1, 2, meaning by we want to know 2c0, 2c1 and 2c2. Again, there is no need of calculating each three of them independently by the integral formula. Let us use the two properties we have in hand. 2c0 is same as 2c2 and sum of these three is 1. So 2c0 plus 2c1 plus 2c2 is 1, and 2c0 is same as 2c2. The simplest to derive will be 2c2. Let us derive the value of 2c2 from the definition of NCI. So 2c2 is given by minus 1 raised to 2 minus 2. n is 2 and I is also 2. So minus 1 raised to n minus I becomes minus 1 raised to 2 minus I. Denominator is n, that is 2. I factorial, that is 2 factorial, n minus I factorial is 2 minus 2 factorial, which is 0 factorial, which will be 1. And integral 0 to 2, numerator has all the products t minus 1, t minus n. So I get t into t minus 1 into t minus 2 and upon t minus I, that is t minus 2 dt. So it is the integral, the outside the integral it becomes 1 by 4 and 0 to 2 t minus 1 dt. And that is 1 by 4 t square minus t integral, that is t cube minus t square by 2. Limits of the integration are 0 to 1. To 2c2 is 1 by 6, and so 2c0 will also be 1 by 6, and sum of the all Cotes coefficient is 1. So 2c1 becomes 1 minus 2c0 minus 2c1. So 1 minus 2 by 6, and that becomes 4 by 6. And so the weights in our Newton-Cotes integration formula for approximating by quadratic polynomial are w0 is 2h into 2c0, so 2h into 1 by 6, that is h by 3. w1 is 2h into 2c1, so 2h into 4 by 6, that is 4h by 3. And w2 is 2h into 2c2, so 2h into 1 by 6, that is h by 3. And so our integration formula becomes a to b fx dx is h by 3 into fx0 plus 4h by 3 into fx1 plus h by 3 into fx2. And so h by 3 we can take common. Inside the bracket we get fx0 plus 4fx1 plus fx2. And this also can be expressed as, because h is b minus a by 2. So in terms of a and b and h, b minus a by 6, f inside the bracket fa plus 4 into f of a plus b by 2 plus fb, or it can be expressed as h by 3 fa plus 4 into f of a plus h plus f of a plus 2h. And this formula is very well known as Simpson's 1/3 rule. The reason why it is called Simpson's 1/3 rule is because h by 3 is outside the integral sign. So now let us look at the graphical representation of the Simpson's 1/3 rule. So you can look at the graph, the same graph we are taking, the same curve. But now we are fitting a quadratic polynomial to it, and so we have 3 points x0, x2, x1 is the midpoint, and shaded region shows the approximate integral value. And we can make out from the graph that the error region has become much smaller as what it was in the case of trapezoidal rule. Now let us derive a next case, and that is n equal to 3, that is when we are approximating function by a cubic polynomial. So now the number of divisions of our interval a to b will be 3, because cubic polynomial, so 4 points x0, x1, x2 and x3. Our a is x0 and the other points x1, x2 and x3 is equal to b. Again the same thing, let the points be uniformly spaced, equidistant point for our convenience, because the general formula which we have derived of Newton-Cotes coefficients, that we derived using uniformly spaced points. So x1 is a plus h, x2 is a plus 2h and x3 equal to b can be said as a plus 3h, and h is given by b minus a by 3. Now let us directly derive our formula through the Newton-Cotes coefficient formulas. So our integral a to b fx is given by sigma wi fxi, that is sigma wi yi, and now this time wi's are nh, nci's, and n is 3 here, so 3h into 3ci. And let us use the properties. 3c0 is 3c3, 3c1 is same as 3c2, and sum of all these 4, 3c0, 3c1, 3c2 and 3c3 has to be 1. So again we need to derive only one of them, because 3c0 is same as 3c3, 3c1 is same as 3c2, so only 2 of them need to be derived, and sum of all them is 1, so we need to derive only one of them. Again the most convenient in the expression will be 3c3 to us, and so let us derive 3c3. So 3c3 is given by minus 1 raised to, because nci is minus 1 raised to n minus I upon n I factorial n minus I factorial 0 to n t minus 1 t minus n upon t minus I dt. In this let us put n equal to 3 and I also equal to 3. So our ncn is, if I put I equal to n first, so ncn becomes minus 1 raised to n minus n, that is minus 1 raised to 0 which is 1 upon n factorial into n minus n factorial 0 to n t minus 1, t minus last term will be n minus 1, because upon t minus n will cancel. So t minus 1 up to t minus in the bracket n minus 1, that is t minus n plus 1 dt. And let us put n equal to 3. So 3c3 is minus 1 raised to 0 upon 3, 3 factorial, 0 factorial, 0 to 3, t minus 1, t minus 2 dt. And so 3 factorial is 6, outside the integral sign we get 1 by 18, 0 to 3, t into, let us expand t minus 1 into t minus 2 gives t square minus 3t plus 2, and that multiplied by 2 will give us t cube minus 3t square plus 2t dt. And so the integral limits are 0 to 3. So we get 1 by 18, and integral gives t raised to 4 by 4 minus t cube plus t square, limits 0 to 3. So put t equal to 3, 81 by 4 minus 27 plus 9 by 18. So the answer is 1 by 18, inside the bracket 81 minus 108 plus 36 by 4, and so result is 9 upon 18 into 4. So 3c3 is 1 by 8, and once 3c3 is 1 by 8, 3c0 is also 1 by 8, and sum is 1, so 2 times 3c1, 3c1 and 3c2 are same. So 2 times 3c1 is equal to 1 minus 2 times 3c0, so 1 minus 2 by 8, so 1 minus 1 by 4, that is 3 by 4. So 3c1 and 3c2 both are equal to 3 by 8. And so our weights will become W0 is 3h into 3c0, so 3 into h by 8. W1 is 3h into 3c1, so this becomes 3 into 3h by 8, so 9h by 8. And W2 is also same 3h into 3c2, which is also 9h by 8. And W3 is 3h into 3c3, that is 3h by 8. And so the integration formula obtained by fitting a cubic polynomial gives us a to b fx dx is given by 3h by 8, where h is b minus a by 3, fx0 plus 3fx1 plus 3fx2 plus fx3. This formula is known as Simpson 3 by 8th rule. The reason of it being called 3 by 8 is again probably that as outside the bracket we have the coefficient of h as 3 by 8, and this can be expressed as a to b fx dx as 3h by 8 fa plus 3 into f of a plus h plus 3 into f of a plus 2h plus f of a plus 3h. And we can have a look at the graph, again the same graph, but now the division are 3 subintervals, and you can look out from the shaded region and look at the error region, which is quite small. Similarly, one can fit a biquadratic polynomial n equal to 4. We will not derive the coefficients here, but they can be derived on the similar lines, and we get the formula which is obtained is a to b fx dx is approximately 4h by 90 in the bracket 7 times fa plus 32 into f of a plus h plus 12 into f of a plus 2h plus 32 into f of a plus 3h plus 7 into fb, where h is b minus a by 4, and this formula is called Boole's rule. If we further proceed ahead and divide the interval into 6 subdivisions, that is n equal to 5 here and 5 subdivisions, 6 points, then a to b fx dx is 5h by 288, and in the bracket we get 19 fa plus 75 f of a plus h plus 50 into f of a plus 2h plus 50 into a plus 3h plus 75 a plus 4h plus 19 fp, where h is b minus a by 5. So this is how any order integration Newton-Cotes integration formula can be derived from the Newton-Cotes coefficient. We will see in our next module the error analysis of Simpson's 1/3 rule and Simpson's 3 by 8 rule, and then we will also derive the composite form of these rules. Normally in practice, the higher order integration formulas are not applied, and final subdivision is achieved through dividing the interval into subintervals and applying the composite form of these rules, because quite stable results can be obtained. Even in the application of higher order formulas, one very big constraint is that you have to divide the interval into, I'll say, multiples of 4 or multiples of 5. Coefficients also are becoming larger and larger as we go to approximating function by higher degree polynomial, and so it is more convenient to smaller order integration formula, and the iterative technique of dividing the interval into different subparts and applying the composite form also can achieve quite good accuracy. So bye till then, we meet again.